9.4, example 4. In this example, we're going to look at finding the radius of convergence of just more series. The main difference is now we have a factorial involved, so it gets a little tricky, but that's still no big deal. So again, I want to find the radius of convergence. I can't think of anything to compare it to. Doing the absolute value is not going to do much. So I'm thinking the ratio test. So we write the limit as n approaches infinity of absolute value a sub n plus 1 divided by a sub n. This tells the grader, or it tells me as the teacher, that you're about to use the ratio test. If you write that down, usually you can get a point or two on the AP test just for writing that when you're working with series. So we have, this is going to be n plus 1 factorial times x to the n plus 1 divided by n factorial x to the n with absolute value bars. So before I go any further, I need to give you a quick little lesson on how factorials work. So factorials, if I have 5 factorial, for example, is going to be 5 times 4 times 3 times 2 times 1, and you get a number. 20 factorial is going to be 20 times 19 times 18 times 17, all the way until you get down to 3 times 2 times 1. So if I have 100 factorial, that's 100 times 99 times 98 times ... times 3 times 2 times 1. Always till you go down to 3 times 2 times 1. Or really till you get down to 1. So if I have, let's say, n factorial, that's going to be n times n minus 1, because you minus 1 from the pattern. N minus 2, because 100 minus 2 is 98. And you keep following that pattern until you get down to 3 times 2 times 1, because n has to be a number. So even if you're at 10 million, you'll eventually get down to 3 times 2 times 1. So if I have n plus 5 factorial, it's going to be n plus 5. Then you take away 1, so n plus 4. Then take away 1, so n plus 3. N plus 2, ... all the way down to 3 times 2 times 1. So that's a little review on how factorials work, which is going to help us in this next step. So what we're going to do here is we're going to start splitting things apart. So this is going to be the limit as n goes to infinity, absolute value, n plus 1 factorial. Well, notice that I have an n factorial down here. So if I can get an n factorial in the numerator, they'll cancel. So this is n plus 1 times n factorial, x to the n times x, all divided by n factorial x to the n. So then the n factorials cancel, the x to the n's cancel, and I'm left with the limit as n goes to infinity, absolute value n plus 1 times x. Alright, well, I get infinity. And infinity is definitely larger than 1. So because it's larger than 1, this series is going to diverge. And we can kind of expect that because every time you increase n, the numbers are just going to get bigger and bigger and bigger, and you keep adding them up. So if you diverge, then your r, your radius of convergence, is 0. Okay, on your own, I want you to give this a try. Try to find the radius of convergence of this series. All right, let's go give it a shot. So this is the limit as n goes to infinity, and then a sub n plus 1 divided by a sub n. So we get this is the limit as n approaches infinity, absolute value, n plus 1 factorial, x minus 4 to the n, all divided by n factorial, x minus 4 to the n. In the numerator, I should have a plus 1 in the exponent. So then we're going to go ahead and split that up. So we get limit as n goes to infinity, absolute value, n plus 1, n factorial, x minus 4 to the n, x minus 4 to the 1, all divided by n factorial, x minus 4 to the n. Now it's good practice to start splitting up exponents with these because you do want things to cancel. So these reduce off, and I'm left with the limit as n approaches infinity, absolute value of n plus 1 times x minus 4. I plug in infinity for n, and I get infinity, which is bigger than 1. Therefore, my summation diverges. which means that r is 0 because there's no convergence, so the radius of convergence is 0.